We're going to get into water now. Water is the only element that actually changes form in the atmosphere. It can go from a liquid to a solid to a gas and back and forth. And that water complicates our cycle and what the atmosphere is willing to do. The book talked about atmospheric rivers this week. And one of the things that's interesting to see on the charts like this, all the moisture being transported across the Pacific and into the northwestern U.S. So if I were to go out of this and just pull this up for a second, we have right here an atmospheric river coming out of the tropical Pacific into and up into Arizona, New Mexico area. You're losing some of its moisture as it's going in there. But this is a tropical river. And you can see one up to the north going up towards Alaska. So these areas are just showing all this moisture coming up and across the tropical Pacific here. If we were looking at it bowed upward into the California area, where you getting tremendous rainfalls in the mountain or tremendous snow up the top of the mountains and all. But instead, we're just getting it, the edge of it, coming into Arizona, New Mexico here. But that is giving some decent precip out there. So that's an example of an atmospheric river. And this chart is called the water vapor image at the mid-level, which is about 15,000 feet up or so. But it's an excellent image as far as being able to look at what is going on in the atmosphere as far as water. So go back to the slideshow here, and we'll start from the current slide again. And we'll move on now, since we've just seen the atmospheric river in real time, to how much water is actually in the atmosphere at any given time. Well, distributed over the globe, if you poured out all the water in the atmosphere, it would come out to a depth of about 1 inch. Not a lot, but still, it's there. So, and water is continually entering the atmosphere. Here is the cycle. Water evaporates over the ocean, condenses on the clouds, comes back down as precip, some of it into the ocean, some of it maybe into land. Oh yeah, trees, photosynthesis, evaporation from the land itself sends moisture back up as well into the clouds. And some of the water actually flows all the way down into the ground and winds up in groundwater storage. Like if you drill a well and you want to find a water table down there, there is some water down there that we can get out. So that is the basic cycle of water in the atmosphere. So how does water go about transforming itself? Well, it goes through evaporation or condensation, transpiration, which is just where water is taken up by the roots and then escapes as a vapor. Evapotranspiration is evaporation and transpiration together. Sublimation is just ice or snow becoming a vapor without transitioning to a liquid first. Say that was what happens when you see frost on the ground at night. And deposition would be just like dew. And precipitation is when water falls out of clouds. So humidity, basically, we're talking about describing the water vapor in the air, which varies by minute, day by day, season by season. And there are various measures of it. And we're going to talk about those a little bit. So let's start water vapor. Well, it's a vapor. So any vapor, any gas has a pressure. Water vapor typically can make up about 4% of the atmosphere's mass, but its pressure is called vapor pressure, water vapor pressure. And it can increase the more water vapors in the air and decrease the less water vapors in the air. Then there's a quantity called mixing ratio. Mixing ratio is the mass of that water vapor in the air compared to the dry air that came out of some area, we'll say some cube in the atmosphere, that contained the water vapor and that dry air. When you subtract the water vapor out, and compare it to the amount of dry air left, that's the mixing ratio. One slight difference, specific humidity, instead of comparing it, the water vapor, to just the dry air, you're now comparing it to the whole mass of air. So they're very close, but they're not always equivalent. So when you want something else here called saturated air, what the heck is saturated air? Well, think about it. If you have a water molecule, and there's a whole bunch of them, and they're getting to the point where they begin to condense. And they're becoming, instead of being vapor, they're going into liquid. Right at that point, some of the molecules are liquid, and some of the molecules are still gas. That's the saturation point. Because some of the molecules are transitioning into liquid, and some of the molecules are transitioning back into gas. When they're at an equilibrium state, that's where saturation occurs. So every term we've just talked about, vapor pressure has a saturation vapor pressure, mixing ratio, specific humidity, all of that. One of the interesting things about this is that when you heat air, the water molecules begin to move faster. It increases their kinetic energy. That means they're able to escape from the water easier. They go back into a vapor. So that means that the hotter the air is, the more water it takes to reach saturation. So here we look at a table. When you get up here to pretty high values, it takes a heck of a lot of water to make it reach saturation. The vapor pressure has really gone up. When you're really, really cold, even today or even the wintertime, you're not doing as well that way. You don't need as much water. So if you had exactly the same amount of water one day and the temperature was 30 degrees, and we'll say the relative humidity was 70%, the next day you had the same amount of water, but the temperature was 80 degrees, the relative humidity might be only like 5 or 10%. So that change in temperature, without changing the amount of moisture in the air, the amount of water vapor, can cause a major difference in the relative humidity. And relative humidity is just that, vapor pressure per saturation vapor pressure times 100. So you're basically saying, okay, how much more percent of water can this air hold before it becomes saturated? If it's at 100%, it's saturated. If it's at 75%, it can still hold some more water. Or the temperature could drop, and then it wouldn't be able to hold as much water. That's one of the things. If you lift an air parcel that's at 100% relative humidity, as that parcel is rising, it's cooling. So some of that parcel has got to condense out into liquid water droplets because it can't hold it anymore. As that, you can't have a relative humidity. You don't normally get relative humidity above 100% in the atmosphere. So instead of there being so much water vapor, some of that water vapor had to transition into a liquid. This is just a graph looking at temperature versus relative humidity. The lower the temperature, many times the higher the relative humidity is. That's why the relative humidity is typically the highest in the morning and the lowest in the evening. Dew point's just another measure of moisture, as one you see on weather maps all the time. It's basically the temperature of the air has to cool if nothing changes to reach saturation or form dew on the ground. So when the dew point and the temperature are the same, we have 100% relative humidity. And you can see here an average dew points for January. Look at it. It's less than 20 degrees over Ohio. In the summertime, on the other hand, it's, up into the 60s. So there is a huge difference in the amount of moisture in the air between January and July. And because we're so much warmer in July, the air can hold that moisture. Notice how in the mountains out west and stuff, it stays relatively constant. So as the air becomes saturated, you begin to form clouds. So they're basically little tiny water droplets. Now, we're going to talk a little bit about stability. I don't want to confuse you, but I want you to understand this because we're going to talk about it a lot. You have an air parcel right here. Here is the air temperature around that air parcel. So if you push that air parcel upwards here, and it was colder than the surrounding air, that air parcel is going to sink back to where it came from. If you push it downward here and it was warmer, it's going to want to rise up back to where it was. So the whole idea of stability is this air parcel colder or warmer than the air around it? If the air parcel is colder, it's stable and it's going to want to sink. If the air parcel is warmer, it's unstable and the parcel is going to want to rise. And you can see that here. And the more, it's not just a rising slowly necessarily, the more the air parcel is warmer than the surrounding air, that air parcel is going to accelerate upwards. That's why in thunderstorms, we can get velocities over 100 miles an hour because the air is very unstable. So the air can cool, we learned it last time, at 9.8 degrees Celsius for 1,000 meters. Now, another condition, if you have moisture in that air and the air becomes saturated, what happens? Some of that moisture, that water vapor, has to condense. When it condenses, it releases heat. And when it releases heat, that means the air isn't able to cool as fast. So it only cools at about 6 degrees in moist air, not really warm. So that's a big difference. That means if the parcel is saturated, maybe it's unstable compared to the air around it, whereas if it had been unsaturated, it might be completely stable. There are some things that cause air to rise. Convection would be one. Frontal uplift, warm or cold fronts can push the air up. Mountains can push it upwards. And then you get the lifting condensation level, which is just the altitude of the air being pushed up a mountainside, or maybe just by a front coming in or whatever, lifting a parcel of air. It's cooling at 9.8 degrees Celsius. That air holds so much moisture in it. It reaches the saturation vapor pressure. It begins to condense. At that point is where the cloud forms, and that's the lifting condensation level. Mountains. So you're sinking the air down, so it can cause what they call mountain wave shadows. And then you have your convergence of winds. All of this is just part of the moisture flow. So let's take a look at just a couple little things here. This is the current dew points. Look at these dew points here in Ohio right now. It's 50 degrees, but 18-degree dew points. So let's take a look at what it had been. Earlier this week, we had dew points around 50 and a temperature around 50. So you had a lot more moisture in the air and it probably very high relative humidity. And if you look over here, it was precipitating at that time. All of a sudden, somewhere right about here, the temperature really started to drop and the dew point really took off and went downwards. I would argue that you had a cold front go through at that time that cooled it off, and the winds picked up about the same time over here, so it was probably winds all of a sudden shifting out of the northwest, and it got colder. So it's a great way to take a look at these charts and just see how temperatures change and dew points change when a cold front, in this case, went through. The other thing I just wanted to show you briefly is an upper air. Say I took a parcel of air right here, and I cooled it at 9.8 degrees. It's going to follow that solid line right here. And at 500 millibars, it's going to be probably close to 10 degrees colder than the actual air. So now, let's take this air parcel and follow this dash line. This dash line is the wet, moist adiabatic line. And what happens is it gets much, much much warmer. So you can see if that parcel ascends dry adiabatically, it's stable. If it descended as moist adiabat, it's unstable. So let me know if you have any questions about any of this.